Welcome everybody to our next lecture in our series of Les lectures on emergent electronic properties at interfaces. Today we are privileged to have Allan MacDonald, who is the Sid Richardson, I think it is a professor of physics at the University of Texas at, Sid Richardson Foundation Regents Chair. So he's an item of furniture at the University of Texas at Austin. Allan is one of the world's leaders in the theory of interacting electrons in interesting situations, especially lower dimensions and high magnetic fields and in twisted moire and related structures. He is published on a wide variety of interesting systems. His work has been recognized by fellowship in the American Physical Society, the National Academy of Science, the American Academy of Arts and Sciences, and by the 27, I think it was, Buckley Prize of the American Physical Society. And today he's going to talk about, I believe, electrons in graphene, twisted graphene, and related systems. And before asking Allan to start his lecture, I will just remind everybody that this is the first of two lectures by Allan. The default is that the first lecture should proceed without questions, except if there's an urgent issue of clarification. Write your question in the chat window, and if I think it's necessary, I will interrupt Allan and ask him to and repeat the question so that it can be clarified for everybody. But otherwise, hold your questions until the end of the second lecture tomorrow, when there'll be ample time for questions. So with that, take it away, Allan.
Okay, so my screen is still visible, is it? Mark?
Yes, it is.
Okay. So yeah, my lecture today is actually going to be about transition metal dichalcogenide moire systems. So these are artificial two-dimensional crystals in which people are recently starting to see a lot of emergent electronic phenomena, lots of strong correlation phenomena. I'm going to talk in my next lecture about more recent work on graphene moire systems, which are the moire superlattice system that's been most heavily explored. But today I'm going to talk about TMDs. So this is introductory. This lecture is mainly based on several papers listed there, written with Fengcheng Wu when he was a student at UT Austin with other colleagues. And I might have time to touch on some recent work by, together with Mattia Angeli who's an exchange student from CISA. So my lecture has 4 parts. First, I'm going to talk about moire patterns and about the recipe for making a model that describes the physics and the relevant energy range in these systems, which is basically an adaptation of the envelope function commonly used in semiconductor physics. Then I'm going to talk about what is actually the simplest case of such a model. And it's actually a case that is commonly applied in these transition metal dichalcogenide systems. As I'll mention, the transition metal dichalcogenides, and I list at the top the chemical compounds to which this work is relevant. When they're thin to a single layer, they are two-dimensional semiconductors, and so that's, we'll be looking at, two-dimensional doped semiconductors, if you like, and moire superlattices in those systems. After I finish, I'll spend most of my time talking about this simplest example, which I call a one-band case. I'll explain what I mean. And I'll spend a lot of time talking about how the properties of the moire superlattice depend on twist angle between layers, which is used to create the Moire pattern. And then I'll talk a little bit about some other examples that are not less explored, at least experimentally so far, which are a little bit more richer models. And so this first part is going to be all about the properties of electronic quasiparticles, fermions, in artificial two-dimensional periodic systems, electrons that are strongly correlated. The final part will be about excitons, bosons. So excitons are easy to study optically in these two-dimensional direct gap semiconductors. And they're bosons, of course, and they are actually strongly interacting bosons. So they're interesting both for their own sake and as probes as a convenient optical probe of the electronic quasiparticles. So let me start. First of all, let me just say something about Moire superlattices, Moire patterns. And so basically this pattern is made from a slowly varying stacking. Which I'll characterize by the ways in which two weakly coupled lattices can be stacked in terms of a vector, which is displacement of one layer relative to the other. So of course, these two-dimensional semiconductors is very important for this Moire, for the Moire superlattices, that they're van der Waals materials with very weak interactions between two-dimensional layers. And so we'll be talking mainly about bilayers stacking two-dimensional layers. And you can characterize all ways of stacking by just moving one on top of the other. And if you can make Moire patterns, it turns out, if the two-dimensional crystals have different lattice constants, or if you twist one relative to the other. I'm going to imagine, just to keep things simple, that we're interested in the case of where we form the Moire pattern by twisting the layers relative to each other. And so you can imagine, if I take one layer and rotate it around some origin of coordinates by some angle theta, then for small angles theta, this is okay. So R goes to R minus plus theta y minus theta y times theta x, or R goes to R plus theta R cross Z. Or that's actually should be Z cross R, but let's put a minus sign there. So if you, as you can easily understand, if you take one layer and rotate it relative to another, if you're far away from the axis of rotation, you will actually move a large distance. The amount you move is just proportional to r, but the relative change in the coordinate is small if the twist angle is small. And so locally, the displacement of one layer relative to the other is changing slowly. And so in semiconductors or semi-metals, when you have a system that depends on some parameter that varies slowly in space, there's a standard way of dealing with it. And the way, one way of building models of these moire superlattice is just to follow that kind of recipe. So this kind of approach is used, for example, in semiconductors or semi-metals to describe the influence of strains or dopants, or maybe some gates on the electronic properties. And the idea is simple. So imagine I have a system that I can describe by some kind of a tight binding model. So I have a tight binding model Hamiltonian. It depends on K. Let's say the states that I'm interested in are all near some particular point in momentum space. Then I can write this Hamiltonian as H of K, which is some reference lattice vector. This is supposed to be lowercase, and this is supposed to be uppercase. This uppercase letter is supposed to be a wave vector for a block Hamiltonian that is, in our case, it's going to be, the reference wave vector is always going to be at the corner of the Brouin zone of the triangular lattice. So, because the low energy states are all at wave vectors near there. And so we write the Hamiltonian as the Hamiltonian at that point, plus another term that describes how the Hamiltonian changes when I move away from that point. And in the envelope function approach, when the Hamiltonian actually depends on a set of parameters, let's call it P, which might depend on position. That's the case we're interested in. Those parameters are going to be this stacking vector D. So the Hamiltonian depends on position, and let's call this correction. And if it's varying slowly enough, then I only need to include that effect in the Hamiltonian, its effect on the Hamiltonian at the reference wave vector. And then, of course, the wave vector difference Hamiltonian, this correction to the Hamiltonian will, in general, the Hamiltonian will depend on position. So if we go back to coordinate representation, this Q goes into a derivative operator. So that's the rough idea. And So we will follow that recipe for the Moray superlattice. Last time, or day before yesterday, in the first lecture on Moray superlattice properties, Leon discussed the case of graphene single layer and twisted bilayer graphene. For the case of single layer graphene, the tight binding model is a tight binding model with two orbitals. So it's a two-band model. And the only orbitals you keep when you just need to describe the low energy physics of graphene are carbon pi orbitals, PZ orbitals, one for every lattice site, and there are 2 lattice sites per unit cell. So if you write down a tight binding Hamiltonian in that representation, then simplest model, you only include hopping from one sublattice to the other on the graphene honeycomb lattice. The energy of the isolated pi orbital you normally take as the 0 of energy. And so it turns out if you expand this, Hamiltonian near one of the Dirac points, then at the Dirac points, the hopping between the pi orbitals vanishes. And so this becomes just minus I h bar v q dot grad, okay, in coordinate representation. And so that's the that's the tight binding Hamiltonian for graphene, single layer graphene, and that's the Hamiltonian that you would use for single layer graphene if you were interested in low energy physics and you had some perturbation. For example, a common one would be from electrical gate, where the Hamiltonian actually has a term, a potential energy term, let's say, which varies slowly as a function of position. Okay, so so that's the recipe we're going to apply to TMD Morays. And I want to consider the case, for example, of tungsten diselenide on molybdenum diselenide. So here I want to make the remark that in these transition metal dichalcogenides, it turns out that the lattice constant depends almost entirely, to about a part in 1,000 or several parts in 1,000, on the chalcogen, on the group 6 element that's part of the compound. And so these two materials have practically the same lattice constant. So things would change a little bit, but not in any essential way. If I talked about, for example, a moray formed by tungsten diselenide on molybdenum disulfide, in that case, even without a twist, you would get a moray pattern. But I will just talk about the moray pattern case. So in this case, you know, we know from the physics of these materials that Let me draw it over here. Okay. Vertical axis here is energy. I'm drawing the energies at which there are states. First point in trying to make a model of this system is that the top of the valence band, the states at the top of the valence band are in the tungsten layer, not in the molybdenum layer. And we want to make a model then of the top of the valence band of tungsten diselenide as it is disturbed by the molybdenum diselenide underneath. And so we know that to a reasonable approximation, I'll write it in momentum space, that if I look at the valence bands of isolated tungsten diselenide, so these are states at the top of the valence band. This is the conduction band. I'll come back to these states later. These states, it turns out, in momentum space, I'll talk about the lattice constant, lattice in a minute. They're localized at these Brouin zone corner points in momentum space. That's where the top of the band is. And if I expand the band around there, it has a parabolic maximum. So if I measure momentum from the Brouin zone corner, the holes have a parabolic band Hamiltonian. Turns out there are two valleys, K and minus K, that are not related by reciprocal lattice vectors. So they're inequivalent wave vectors. They're different states. And but if I look at one of these momentum as indicated here, there's a large spin orbit splitting. In the case of tungsten diselenide, it's around 0.4 eV, and that's bigger than any of the scales that we're interested in. And so we can concentrate just on these states. And it turns out that the way spin orbit splits in these systems, because of the symmetry at the K point, these states are D states. They're tungsten d orbitals with azimuthal angular momentum, definite azimuthal angular momentum, because there's enough rotational symmetry, C3 rotational symmetry, that these are basically azimuthal angular momentum eigenstates. And that's what allows the spin orbit coupling to produce such a large splitting. Usually, most wave vectors in a material, the spin orbit coupling only has effect of the spectrum on second order in perturbation theory, but here, because there's a splitting, because these states have definite azimuthal angular momentum, they're split at first order in perturbation theory from the L dot S spin orbit coupling operator, which means the spins of these states they have spins oriented along the plus or minus Z direction. And what's most important for us is that there's only one spin at each momentum. The state in the other valley, of course, is in the opposite momentum. In the other valley is the time reverse counterpart. So that state has opposite momentum and also opposite spin. So spin and momentum are locked together, as is common in systems without inversion symmetry. I'll talk about the structure in a minute. So I can, I can choose to view these states near this momentum, label them by their spin or by where they're near in momentum. So let's just label them by spin. So in an isolated single layer tungsten diselenide, then for every momentum, you have two states labeled by spin. They have, if you do a particle hole transformation and count these as holes, then they would just have normal E equals, K squared free particle dispersion. So, okay. So what does the Moire potential do to that? So for every momentum, for every momentum in this case, before we add the weak coupling between the layers that produces the Moire pattern, we only have one state at each momentum. So the tight binding model Hamiltonian I was referring to before just is a 1-by-1 Hamiltonian, a number, the energy of the state at the reference wave vector, and the energy of that state depends on parameters. It depends on D. That's the parameter that we're interested in. And so the effective Hamiltonian, then, if I include the dependence on stacking, is and I do a particle hole transformation, is just H is K squared over 2M plus some real number, which I can think of as a potential, which depends on the local stacking. So nothing could be simpler. And so that's the model for a Moire in single layer TMD. We just now have to say something about how we're going to model how this energy depends on D. And so let me say something about that, or maybe I can still use this. So at this point, we always measure energy from the top, measure momentum from the Brouin zone corner, from the top of the band. So we just, we can just say energy goes like K squared, free particle. But the energy at the top of the band depends on what the stacking is. And I want to make the claim then that if I translate the layer underneath by a lattice vector, you can't tell. So that means this shift in the energy of the top of the valence band has to be a periodic function of D. And that means I can expand it in terms of reciprocal lattice vectors of the crystal. And so let me do that. Eg, e to the I, G dot D. Now I'm going to make some simplifications that can be relaxed. So first of all, this reciprocal lattice vector expansion of the stacking dependence of the top of the valence band has a spatial average term. We can just choose that to be 0, just a choice of the 0 of energy. And so this in principle is the sum over, let's say, G not equal to 0. And if we think that this dependence is smooth, and there is a reason to expect it to be smooth, the reason is that the distance between atoms within the van der Waals layers is much bigger than the distance across the van der Waals gap between the TMD layers. And that will tend to smooth out any sharp variations in this potential. And so simplest approximation is to just include the first shell of reciprocal lattice vectors. So I'm going to talk now and again about the structure of the TMDs. So I'll refer to this little cartoon. This is looking down on a single layer TMD. First of all, it's a triangular lattice system. So I've drawn it in terms of hexagon primitive cells with the metal atoms, tungsten, let's say, at the middle. And the Bravais lattice is a triangular lattice. I guess it's written there. Actually, the sketch has the one of the Bravais lattice vectors, as you can tell, of the triangular lattice in the y direction, and let me so let me use this also as a picture of the reciprocal lattice. In the real space structure, there are metal atoms at the center of these hexagons, and there are chalcogen atoms looking from the top on one half of the sites around the ring on these trigonal sites, and they're above each other. There are 3 in a plane above the metal plane and 3 in a metal below the metal plane, in a plane below the metal plane. But for reciprocal lattice, of course, we can forget about this decoration. And the reciprocal lattice looks just the same, except for a rotation by 90 degrees. So we can also think about it, a coordinate system in which these points represent reciprocal lattice vectors. And so the first shell would be the reciprocal lattice vectors here, 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 here. There are 6 of them. And so let's say we expand just in terms of that 6. And so that's what these VGs are. And so we can simplify this expansion a lot. There are 6 of these. Let me label those 6 reciprocal lattice vectors the way I've drawn them. Sequentially, let's say 1, 2, 3, 4, 5, 6, where this is G equals 0 at the middle. V, the function we're expanding, is a real number. So that means V of minus G is Vg star. So that means if I know V1, I know V4. But system also has a 120-degree rotational symmetry. And that means that the coefficients of these three reciprocal lattice vectors differ by 120-degree rotation, have to be the same. And so V4 is V1 star, because V is real, and V2 equals V4 equals V6 from rotational symmetry. And so that means that this V of D, if you know it for one reciprocal lattice vectors, then you know it for all. So there's one complex coefficient, if you say this potential is smooth, that characterizes the dependence of energy at the top of the valence band on stacking. When you place one TMD on top of another TMD that doesn't have any states in the same energy range. Right. So how do we turn that then into what happens if I have a moire pattern? So let me just write this down again. VD is sum over first shell of reciprocal lattice vectors, coefficients, coefficients times plane wave coefficients. But in the moire pattern, the stacking varies linearly in position. So let me put in the expression for the displacement of the bottom layer that you get when you rotate it. And so you can see that I can write this as sum over G, coefficient Pg, I e to the I r dot G cross theta Z. So these six atomic scale reciprocal lattice vectors get translated in the moire pattern through this twist angle into an effective potential that has an expansion that is periodic in a lattice that has these as reciprocal lattice vectors. And so you can see that the size of the reciprocal lattice for the moire pattern is smaller by a factor of theta. It's also, in the case of the twist, rotated by 90 degrees. And so that means that this is, in the moire pattern, you have a potential that's a function of position, and the potential has lattice periodicity. The lattice vectors of the moire lattice, the lattice they're also a triangular lattice rotated by 90 degrees because of this cross product. And the lattice constant is simply larger by a factor of 1 over theta. So what you get then is the states near the top of the valence band are described by a free particle in a triangular lattice symmetry periodic potential. And okay. And so this periodic potential is characterized, as I said before, if the potential is smooth by one complex number. That complex number determines where this potential has its minima. That complex number, magnitude and phase, can be determined by fitting to ab initio band structure. That's normally the way we do it, and basically, if you do an ab initio band structure, this is my picture again of the structure of a single layer, and you can imagine if you locally move the layer underneath it relative to it being to stack directly on top. For example, if I take the layer underneath and drag it over here so it's under the metal, that's going to take a negatively charged ion and put it under the metal, the tungsten, and the electrons in the tungsten will see that as a repulsive potential. So that's where the maximum actually of the occurs. And the simplest way to think about the potential that binds holes is that it's repulsive potential from the ions underneath. Although if you look under the hood, then you will realize that this effective potential is coming partly from these electrostatic potentials communicated from one layer to another, and partly actually from level repulsion from states near the top of the valence band of the molybdenum. So what was I going to do next? Yeah. Okay. Yeah. Okay. So so at least by this argument, if you take a single layer tungsten diselenide, put it on single layer molybdenum diselenide, and twist it by a little bit, you will get a quantum particle in a periodic potential, and you are free to choose the period of that potential. And so I want to, you choose it by varying twist angle. And so the next thing I want to talk about a little bit, is how the properties of this artificial Moire superlattice system, which you want the twist angle to be small for this envelope function description to work. So we're really talking about small twist angles, and we want the twist angles to be, let's say, less than 5 degrees or so. Now I want to say something is, if you have a small twist angle, does the bandwidth of these artificial bands created by this artificial periodic potential, are they narrow bands or broad bands? Are these metals or what are they? And so let's look at that. So now this V of R is just this effective potential. And this is, I'm thinking of it as a potential for holes. So I've done a particle hole transformation. And so it must have a potential minimum somewhere. In fact, as I mentioned a moment ago, typically it has a minimum when the metal is on top of the chalcogen. But I can make the lattice constant as big as I want it to be. So there must be, you know, if the Moire pattern's lattice constant is big enough, then there must be possible for the electrons, many electronic states, to be localized near the minimum of the potential. So let's expand V of R, choose the origin at the minimum of this potential, and look in just one of the Moire periods and do an expansion. It turns out the symmetry is such that to quadratic order, the expansion around the minimum, this constant I'll throw away in a moment. The expansion around the minimum is, you know, isotropic to order R squared. So it's just a 2D harmonic oscillator. If there's no tunneling if the lattice constant is big enough that there's no tunneling from one minimum to another, then all you have is a 2D harmonic oscillator. And so let's try and figure out what is the separation between those localized states in different unit cells, and how does it depend on twist angle. So these localized harmonic oscillator states are will, of course, as the Moire period gets shorter, broaden into bands. So this is kind of the band spacing when the bands are very narrow. So how can we estimate that? Yeah, so we can, first of all, notice that the coefficient of R squared in this expansion, you know, has to scale with the overall strength of this modulating potential. Turns out that the strength of these potentials is typically in the 50 milli-electron volt range, which is kind of an attractive range because it's big enough for lots of experiments and to not to be too easily overcome by disorder, but small enough that it's smaller than, for example, the energy separation to other bands. These two things, of course, are different, but they are scale in the same way with the external potential. But this coefficient is basically the second derivative of the potential near its minimum. So that means that the potential has to scale. You know, this potential varies on the Moire length scale. So that means it goes down like 1 over the Moire length scale squared. So that means if I multiply this by h bar squared, so h bar omega, of course, is the spacing between the harmonic oscillator scales. So I can write this as h bar squared over m or a Moire squared times v naught. Okay, so this is an energy scale that Leon actually brought up a couple of days ago. Let's call that the W sub n. It's kind of the kinetic energy scale associated with the Moire length, and it's the width of the lowest band in the Moire potential when the bands are broad. But if I define that energy scale, then you can see that means that the energy difference between bands goes like the square root of these two length scales. And what's most important is that this is, since the Moire length is inversely proportional to twist angle, this is proportional to twist angle. As the twist angle gets small, the spacing between bands gets smaller. Okay. Yeah. So we can estimate another length scale. So I'm going to now estimate the width of the band. And in order to do that, I'm going to do it by first estimating what does a harmonic oscillator wave function look like and how rapidly does it decline as it goes away from the minimum. So, there is a natural length scale for harmonic oscillators, as you remember from elementary quantum mechanics. And if you can't remember the formula, you can remember that it's the length at which the kinetic energy scale, uncertainty principle kinetic energy scale, is equal to the potential energy scale. And that gives the formula A oscillator to the fourth is h bar squared over m squared omega squared, or A oscillator is square root of h bar over m omega. And let me write that as square root of h bar squared over m A Moire squared, the length scale we wrote above, and divided by h bar omega. So I have to multiply this by A Moire. And so I see that A oscillator over A Moire goes like square root of W Moire divided by h bar omega. So I should remind you that I said before that the Moire lattice constant is proportional to 1 over theta. This is going to work out right. Yeah. And W Moire goes like 1 over theta squared. H bar omega W more A, sorry, goes like 1 over A more A squared. So it goes like theta squared, the numerator here, and the denominator goes like theta. So this goes like square root of theta. So the, and that means that a oscillator actually goes like 1 over square root of theta. So this, the point is of this is that this harmonic attractive potential in the middle of each period is a lot softer than the 1 over R Coulomb potential that we have near the atoms in real crystals. And as I make theta smaller, the wave function in the moire actually spreads out over a larger distance as theta gets smaller, but the distance over which it spreads relative to the moire period is actually does go down. And yeah.
Okay, so excuse me, Alan, I just wanted to interject that approximately 1 hour has gone by.
Okay.
So that means that you have 31 minutes by my clock until this thing is notionally supposed to end.
So I'm going slower as usual.
But this is great. Just
okay.
Take your time.
Yeah. So the other thing that's important to estimate is the bandwidth. Okay, and let's say the bandwidth, the hopping integral from one atomic site to another. And, we can estimate that in quantum mechanics as a kinetic energy from the gradient of the wave function localized, let's call this Fourier or harmonic oscillator, I'll call it. Okay, kinetic energy associated with the overlap integral between harmonic oscillator states localized in different sites. And so you can see that this has a factor of the natural kinetic energy scale associated with the moire period. But because these wave functions are localized, the product of the two wave functions for the Gaussian wave functions of a harmonic oscillator is maximized in the middle between the two sites. And so this goes like e to the minus a length scale that goes like a moire squared. That's the midpoint between the two sites. Both of the wave functions are small there. Over a oscillator squared. So this is e to the minus x squared over a oscillator squared is the form of the wave function. I think they're if you square the wave functions, there's actually 2 here, and so you can see that this goes like the kinetic scale associated with the moire pattern times e to the square of this ratio I just calculated. And so that goes like e to the minus theta. And so that energy scale very quickly gets small. And there's one other important energy scale that you can need to estimate in thinking about the system. And that is, let's say, the on-site Coulomb energy scale. And that scale is, the Coulomb self-interaction energy of harmonic oscillators, and it will go like E squared over the oscillator length. And so this actually goes like that actually goes like square root of theta. Okay, so so there are a bunch of energy scales that get small in different ways. They get small. The one that gets small fastest, that gets small in an exponential way, e to the minus twist angle, actually. I think I did this wrong. E to the minus 1 over twist angle. So the bands at small twist angles get extremely narrow because electrons have to tunnel a long way from one minimum to another. There are some things that are unusual. Let me just summarize all those energy scale estimates. H bar omega, that is the band splitting. It goes to 0 like theta. So U, the on-site Coulomb interaction, also goes to 0 as theta goes to 0. But it goes to 0 more slowly. It goes to 0 like square root of theta. And that means the very small twist angle regime is a multi-band, strongly interacting system. And so it's not the Hubbard model, although there seems to be a large range of intermediate twist angles where H bar omega, if you put in the numbers, is much bigger than U. But the bandwidths can be tuned simply by twist angles. As theta goes to 0, they get small extremely quickly. So this system, these properties have to do with the fact that the attracting potential near the minimum is softer, and softer than Coulomb potential. And there's another related thing I just want to mention briefly in passing. And that is that these calculations are actually calculations of the quasi-particle energies when the bands are empty. And there are no free particles to interact. Usually when we try to understand a strongly interacting electron system, we first do DFT and hope that DFT sort of gets the average occupancies of the orbitals more or less right, because it's equally true in atomic physics that the strongest interactions are simple electrostatic interactions. And so you have to kind of include that at a mean field level before you start to add correlation effects. And so in these Moray superlattice narrow band strongly correlated systems, that will be doubly true. And these estimates that I've been discussing, these bands will get can get strongly normalized in certain regimes as you fill up the bands. Another thing I should mention is that I've been lying a little bit. Turns out there is another important length scale. This is a length scale associated with structural relaxation. If you twist one layer relative to another, the atoms will try to relax to get the energetically preferred stacking arrangement. And the elasticity of the of the 2D lattices pushes against that relaxation. So it turns out that there's a natural length scale, which is proportional to the interaction energy, the dependence of the just total energy of the bilayer system on stacking. And so I've called that energy scale U naught. If U naught is strong, there will be a strong tendency for the structure to relax to whatever local configuration, which is usually one of the simple ones, whichever one gives the lowest energy. So if that is strong, then this, basically system will typically end up with AB and BA domain regions, stacking regions separated by a domain wall in the stacking arrangement. And the length scale of that domain wall is another length scale that I've been ignoring so far, but can be important. And this length scale is extremely long in graphene compared to typical situations because the interaction between energies, because it's a van der Waals interaction, is small, and the elastic constants within the graphene layers are extremely large. So that makes this length quite large. And the length is shorter in the TMD systems. And what this lattice relaxation does is basically introduces, changes a little bit the spatial pattern of the effective potential experienced by the electron. Okay, let me go back to my outline here and remind myself what I was going to talk about. Okay, so yeah, so that is the simplest case where what I've talked about so far is where I know in the moire that the electrons are only in one of the two layers. So the only degrees of freedom are the degrees of freedom of that, of the layer that has the higher energy valence band, let's say. But what if you make a moire pattern between two identical layers? This is what we do with graphene, for example. So here's one example. Let's say I have 2D crystal molybdenum ditelluride, and I have another one, and I make a twist angle between them. And I'll say in a moment why I picked this compound. But what happens now is, I follow the same argument I had before. I have standard kinetic energy. I have two spin states locked to momentum states. But now I can't say the electrons are in just one of the two layers. So I have to allow a band state I have to allow a layer degree of freedom. So electron is, has a spin, but it also can be in the top layer or the bottom layer. And there can be tunneling between the layers. So I have to, so the model Hamiltonian, this case has not been realized experimentally, not been studied. The other case, the hetero bilayer case I talked about recently, was talked about originally, where I only need to use a one-band model, has been studied extensively in recent experiments, and people are seeing lots of interesting strong correlation effects that we can talk about in questions if you like. This one's not been. In this one, it turns out that there's a symmetry. The two layers are identical. So if I displace one layer, if I drag one layer, let's say to the right by some distance, it's exactly the same as dragging the other layer to the left. So these potentials for an electron in the top layer and potential for the electron in the bottom layer, they're not independent of each other. Turns out delta T, the tunnel in between the layers, is a complex number. And it turns out by symmetry, it vanishes at two high symmetry points. And I can think about this as, in addition to the kinetic energy, and I have average potential energy, and I also have an effective magnetic field that acts on this layer degree of freedom viewed as a pseudospin. And the layer state, or the layer dependent field, I can, view as an effective magnetic field with a magnitude and direction. And it turns out that if you look in space, that effective magnetic field has a skyrmion. There's one that covers the Bloch sphere, or it's not a Bloch sphere. Here I'm talking about effective magnetic field. But the direction of that effective magnetic field covers the sphere if you integrate over 1 unit cell. So this Hamiltonian is topological in real space. It also turns out it's topological in momentum space. Another case is a HOMO bilayer. In these other cases, it turns out that the coupling between layers, let's say, so this is a two-band model, and this is a one-band model. So this is a HOMO bilayer, a Moiré pattern, two layers that are identical. In this case, turns out that if you look at the gamma point in the two-dimensional Brouin zone, the tunnel in between the layers is much stronger than near the K point. And in this case, it's strong enough that it pushes the top of the valence band, at gamma above the top of the valence band at K. So the low energy states are states at gamma, and it turns out that the splitting between the hybridization splitting between the two layers in this case is a big energy scale, much bigger than other energy scales. And so this reduces to a one-band model. The only relevant wave function at top of the valence band is a symmetric combination of the two layers. And that means, and this is this case we've been working on recently with Mattia Angeli. And that means that the symmetry property that I mentioned before, that means the top and bottom layer potentials are invariant under R go to minus R, now applies in this one-band model to the effective potential energy. And this is a restriction that we didn't have in the first case I discussed. If you add that restriction, it turns out that it requires that the potential, this Fourier coefficient, complex number that I said determined the physics, of the one particle physics, has to be real. And as a consequence, it turns out that there are actually two minima per unit cell. Instead of at the metal on chalcogen sites, at all of the sites, instead of just on these sites in the stacking, at all of these vertices of the honeycomb, you have equivalent potential minima. And so that means that system, which should be very realizable, realizes the two-dimensional honeycomb lattice. So two-dimensional triangular lattice, of course, is interesting because it's got frustrated magnetism and all that stuff. But two-dimensional honeycomb lattice is a bipartite lattice, much more conventional in many ways, and maybe has correlation physics much more mappable to cuprates, if cuprates are described by two-dimensional one-band generalized Hubbard models. Okay, so I've gotten to my end of my talk, except for I was going to talk about excitons, but maybe this is actually a good point to stop. About excitons, I will only say a couple of words. Won't give you any details. So excitons, in the same way, simply experience a periodic potential in the Moiré pattern. And it turns out that the exciton bands are topological if you add an external magnetic field for interesting reasons connected to the fact that you can select valley with momentum, well-known optical property, with light helicity, sorry, well-known optical property of these systems. And they're strongly interacting bosons. Maybe they can be studied for lattice, in connection with lattice boson models. Another thing, and I just heard a talk recently from Atash Imamoglu in Zurich on this topic. It's well known in part of the exciton physics in the absence of a Moiré pattern is that excitons, if you dope a material, the excitons will interact with the dopants, with the carriers, free carriers, and the optical absorption spectrum turns into what are described normally, and this is Imamoglu and co-workers who I think developed this language, Demler, of attractive and repulsive polarons. And so that polaron physics of excitons interacting with electrons is very changed, as we know from these recent experiments, changed in very interesting ways by the Moiré pattern. And also something that's been used already in experiment is optical probes, of course, are always convenient, especially for 2D electron systems, because they isolate them very effectively. And so people are inventing more and more ways that they can use excitons as a probe of what's going on with correlated particles that are present in the absence of the optical probe. So let me just stop there, Andy, and turn it back to you.
All right. So thank you very much for this wonderful talk, Allan. This is a good stopping point, and we have a few minutes for questions. If there are any, write them in the chat, and I'll have a look and transmit them to Allan. And at the moment, I guess I am not seeing any questions, which indicates a massively clear talk and quite possibly that Europeans are getting hungry. So if there are no further questions, then I suggest that we thank Allan and adjourn until tomorrow morning.
Okay. Thanks,
All right.
everyone.
Thank you very much, Allan, and I'll see you tomorrow.
My pleasure.
Thank you.
Thanks.